Question 5.3. Let's first focus on part A. We're going to design a Butterworth filter, low pass filter, and also a Chebyshev Type I filter that meets these specifications. And what are the specifications? The first one is the passband ripple should be up to 3 dB. Passband ripple, and that's well, we show passband ripple AP. So if we have that in dB, because it's a ratio, then I can convert that. So we know 3 dB equals 20 times log of AP to the base of 10. Okay, so we know that if we have, for example, log of x to the base of y equals z, we can conclude that y to the power of z equals x. So I can do the same here. I can write this as log of AP to the base of 10 equals 3 over 20, and that means AP equals 10 to the power of 3 over 20. So the first one. We have also here stop band attenuation of at least 30 dB. Well, we show a stop band attenuation by AS. So here we have 30 equals 20 times log of AS to the base of 10, and we can conclude that AS equals 10 to the power of 30 over 20. Okay, so passband edge, this one, passband edge frequency of FP equals 1 kilohertz. So FP is passband frequency edge, that we usually show that by omega p, the angular frequency. So I want to convert this 1 kilohertz means 10 to the power of 3 hertz. I want to convert this to angular frequency, so I need to multiply that to 2 times pi, so we would have omega p equals 2000 pi radian per second. I can do the same for stop band edge frequency. Well, we show that by Fs equals 7 times 10 to the power of 3 hertz. And if I want to show that convert that to the angular frequency, omega s equals 2 pi times Fs, then it would be 14,000 pi radian per second. All right. Well, now we have all requirements we need. So let's design the Butterworth filter first. Okay, let me put everything here. AP equals 10 to the power of 3 over 20. AS equals 10 to the power of 30 over 20. Omega P equals 2000 pi radian per second, and omega s is 14,000 pi times pi radian per second. All right, now we know the requirements, and based on these requirements, we should the first step, we need to determine the minimum order of the system or the filter. For Butterworth filter, the order of the filter should be higher than or equal to this value, square root of me give some space here. Square root of as squared minus 1 over ap squared minus 1, and divide this by log of omega s over omega p log to the base of 10. If I replace this by the values we got, we have as is 10 to the power of 30 over 20 squared minus 1 over 10 to the power of 3 over 20, 3 over 20 to the power of 2 minus 1 divided by log of omega s, which is 14,000 times pi over 2,000 times pi, okay, which is 1.775. Well, n should be larger than this value. Well, n is the order of the filter, it is integer, so we conclude that n should be at least 2. That's the order of this filter. Second step is to find the cutoff frequency, omega c. And if you check the definition 5.1, this is the first definition in chapter 5, well, it says omega c is the frequency, the cutoff frequency is the frequency where the magnitude of the filter, the frequency response, the filter is reduced to minus 3 dB. Okay. Well, if you check this slide here, we said the passband ripple is allowed to be up to 3 dB, and that means at omega p here, at the passband H frequency, the filter, the magnitude of the filter is already reduced to 3 dB. Okay, so let me write it here. From the requirements, from the requirements here, we already know that at omega p, the magnitude of the filter is reduced to 3 dB. So we can conclude that, let me write this color, we can conclude that cutoff frequency is exactly the passband H frequency, which is 2000 pi. Alright, so this is the second step, and the third step is to find the transfer function. The transfer function of the Butterworth filter, well, we can discuss that how for different orders, but in general, the transfer function, let me write it here. The transfer function for, I would say this is general form for nth order Butterworth filter. Okay, h of s equals -1 to the power of n times p1 times p2 times p3 times pn over s minus p1 times s minus p2 s minus pn. And what is this p1, p2, pn things? These are actually the poles of the transfer function, okay? And each of them can be, like, say we have n poles for nth order Butterworth filter, and pn equals omega c times e to the power of j times j pi times n minus 0.5 over n, capital N, plus 0.5, okay? This is the way we calculate the pole. And how did we get this general form? Well, you need to do some math to get this, but you probably remember from chapter chapter 5. Yeah, it's actually in the chapter 5. You got this h of omega, frequency response, equals 1 over, for Butterworth filter actually it's 1 plus omega over omega c to the power of 2 times n, okay? And if you replace here by, actually I'm gonna find the transfer function using the frequency response, and we know that h of omega is h of s, just s here equals j omega, okay? So if I replace the omega, if I isolate omega, omega is s over j, isn't it? And if I replace omega by s over j, then you would have 1 over 1 plus omega over omega, I'm sorry, and that's actually s over j omega c to the power of 2n, all right? And then this, if I calculate the square root of this value, all right, then that would be h of s times h of minus s, okay, the conjugate of h of s. So if you work with this, you'll finally get something like this. I'm gonna skip this part because that's not about the question, actually not about the chapter even. Just bear that in mind, that for a general for a Butterworth filter at the order of n, this is the general form for finding its transfer function, okay? And let's remove all this stuff to prove that. How do we get this? We don't need that. And all right, so if I calculate the poles and then replace the values in this general form, I can get another general form for second order Butterworth filters. So for, let me move up all this stuff. Then I can write here that the general form of HS for second order Butterworth filter is, as I said, you should find the poles and replace that in the transfer function. Then you get this transfer function for second order Butterworth filter that equals S over omega C squared plus S over omega C times square root of 2 plus 1. This is the general form for transfer function of a second order Butterworth filter, and we know that omega C equals 2000 pi, so if I replace that here, then we would get S over 2000 times pi squared plus S over 2000 times pi times square root of 2 plus 1. And this is the transfer function. And then by this we can say, okay, we have designed the filter, the Butterworth filter we need. Now it's time to find the to design the Chebyshev Type I filter. Let me pause the video and move all the stuff we got from the requirements we got from the previous from the question. All right. So these are all the requirements for the filter we need, the Chebyshev Type I filter. Again, the first step is to find the order of the filter, similar to what we did for Butterworth filter, but this time we use a different equation. Well, in Chebyshev Type I filter, the order of the filter should be higher than or equal to square root, it's actually arc cosine hyperbolic of square root of arc cosine hyperbolic of AS squared minus 1 over AP squared minus 1 divided by arc cosine hyperbolic of omega S over omega P. And if you replace the values in the requirement part here, then 1, we get almost this n equals 1.574, okay, almost. And that means n should be at least 2, or the order of the filter should be at least 2. Well, this was the first step. The second step is to find the omega C, the cutoff frequency. For Butterworth filter, we saw that this omega P equals omega C equals omega P for this case, so this equals 2000 times pi radian per second. The third step is to calculate the ripple control factor. Well, we didn't have this step in Butterworth filter, but here for Chebyshev filter we have it. The ripple control factor epsilon equals square root of AP squared minus 1. Okay, so AP squared is 10 to the power of 3 over 20 squared minus 1, and this equals square root of 10 to the power of 6/20 minus 1, and this equals almost equals 1. Okay, and the last step is finding the transfer function. Again, for this case, I give the general form for Chebyshev Type I filter, and then we need the second order. So I'll give the general form for the second order filter, Chebyshev Type I filter. Okay. Alright, the general form of transfer function for Chebyshev Type I filter is like this. It is minus P1 times P2 times P3 times Pn over S minus P1 times S minus P2 minus P2 times S minus Pn for the case n is odd. Okay, n is 1, 3, 5, 7 or so, and it is 1/1 plus epsilon squared ripple control factor, okay, times P1 times P2 times P3 times Pn over S minus P1 times S minus P2 times S minus Pn. Okay, for n is even, like 2, 4, 6, and so. Alright, so for the case with only 2 poles, because this is a kind of rule that for a nth order Chebyshev filter, there are n poles and no zeros. Okay, so for the second order case, well, for this case actually it's not a general for second order case. This is for the case we are considering, because epsilon here is 1, so we would have P1 times P2 over 2 times S minus P1 S minus P2. Alright, so here we need to calculate the poles, and poles actually require some calculations like cosine of hyperbolic and arc cosine of hyperbolic, so I leave that to you. That's just doing some calculation using a calculator or online websites, then you can find the value. So that's all we actually got for Chebyshev filter. This is the general form of the transfer function, and bear that in mind that it doesn't have any zeros, but it has n poles if the order of the filter is n.